Okay, in this video, I'm going to talk a little bit about different number systems that have been used throughout history and in different cultures. You may recognize some of these number systems that are on this page. Roman numerals we still use. Sometimes you'll see those, for numbering Super Bowls or kind of a fancy way to write the year. You might see Roman numerals. You might also be familiar with tally marks, kind of a more informal number system. If you're trying to keep track of something or count something, tally marks can be more efficient than even what we use are kind of Western Arabic numerals, 0 to 9. Sometimes it's hard to change it through to a 4. So if you're keeping a running count, this tally mark system might be useful. So different number systems have different purposes. Interestingly, a lot of the countries that speak the language Arabic use Eastern Arabic numerals, which are a little bit different, but still kind of a base 10 system like we use. Not all systems work in the same way. You can see Mayan numerals here, and also some indigenous number systems might use a base 20. So what does it mean when we talk about different bases, and how does that affect a number system? So I'm going to show you a couple examples about why we use the number system we do, and what are some other sort of common ones that are also used and how they work. So Roman numerals, which you might be familiar with, XII means 10 plus 1 plus 1, so that's 12. And then IL, this actually means 1 less than L, and L is 50, so it's 49. So it's a way that we can record numbers. They're different symbols for, I is 1. You might know that V is 5 and X is 10 and so on. The problem with Roman numerals is that made actually doing any type of mathematical operations really complicated. There's no sort of intuitive way or algorithmic way that I can add or subtract these numbers. There's no firm rule about whether the bigger numbers, the larger place values, come first or second. So here, 1 comes before 50, and here I've got 1 coming after 10. There's also no rule with the number of digits. So the number of 12 needs 3 symbols. The number of 49 uses only 2. There's no easy way to add this, either vertically or horizontally. So it's difficult to do any sort of operations with Roman numerals. Our number system works really well for operations because of what we call place value. So each digit has a place value, which you've probably learned whether it's in grade 1 or grade 2. We have this ones column, this tens column, this 100 column, which makes doing any type of calculations really easy. 5 plus 9, I've got 14 ones, probably something that you've learned many years ago, so I carry the 1 because that's worth 10. And so it makes doing math really simple because we use this base 10 system, where each place value is a power of 10. So I got 1, 10. Each place value is 10 times as large as the one before it. Well, why do we use powers of 10? Probably whoever thought of this had 10 fingers. And so it made it really easy or simple to count in groups of 10. It was really intuitive. That's why we have 10 symbols, 0 all the way through 9. I don't know why I'm writing these all down. But we've got 10 symbols because we have those 10 fingers. If the guy who'd thought of our numbering system had lost a finger, maybe we would all do every math in base 9. The math wouldn't be different, but the way that we record it or think about it would be. So we use base 10 in almost everything we do in math. But not everything makes sense in base 10. If you think about the way we think about time, we don't use base 10. In time, we might use base 60, right? There's 60 seconds in a minute, 60 minutes in an hour. So we don't use base 10 for time. Our metric system is based on base 10. The imperial system down in the United States is not. Computers also don't like base 10. Computers don't have 10 fingers. So computers think about or interpret numbers a little bit differently. Computers can actually only receive information by either getting an electric signal or not getting an electric signal. So a computer can really take 2 inputs, and we can use 2 symbols, 0 and 1. So a computer actually works in base 2 with what we call binary. Bi is the Greek prefix for 2. You can think about a bicycle. So it's only going to use base 2. So how can we write numbers in binary? Well, my place values, instead of having a ones column and a tens column, my columns in place value are all going to be powers of 2. So I have a ones column, a 2 column, and then it's going to be all my powers of 2. So each place value is worth twice as much as the next one. So if over here I write down our decimal numbers, then we can create binary versions of them. If we take the number 0, that's fine. That's going to be a 0 in the ones column. A 1 is the same thing. So 0 and 1 are the same in binary or in base 10. So over on the left here, I've got my binary numbers. On the right, I have my decimal numbers. Now, I get to a problem. How do I write 2 in binary? I can't use a third symbol. A computer can't take a third input. So I'm going to need to use a 1 in my 2 column, and I've got 0, 1. So I have 1, 2, and 0, 1s, and that makes 2. If I have 3, well, that's 1, 2, and 1, 1. So I'm going to only use 2 symbols. If I get to the number 4, well, again, I can't put a 2 in the 2's column, so it's 1, 4, no 2's, and no 1's. And I could go on from there. Again, we're putting the numbers in our column. So 5 would have 1, 4, no 2's, and a 1. So I still have place value. I can still do operations, but I'm just carrying into the next column every time I reach 2 instead of every time I reach 10. So binary, this is how a computer can read information. The problem with binary is it can take quite a bit of space to write even fairly small numbers. So which is why humans, we prefer not to use it. We like using more than just 2 symbols. If I had the number, I don't know, 19, well, we can write 19 with only 2 digits because I'm only into my power of 10 and then 1s. Binary, it would take me a lot more digits. I've got 116, and I have no 8s, no 4s, and I have a 2 and a 1. So 16 plus 2 plus 1 equals 19. So that's how we can convert between binary and decimals. Binaries, again, is how computers can read inputs. Now, computers don't just use binary. They also sometimes use what's called hexadecimal. So decimal is base 10. So dec is from the Latin number 10. So any kind of word that starts with des, something to do with 10. The word decimate, which means kind of destroy, came from, I think, a practice in ancient Rome where they might kill 1 of 10 captives in war. And so that would be called decimating. Des stands for 10. Hex is the short form for 6. You can think about a hexagon. So hexadecimal, 6 and 10, is base 16. So so now our place value columns will still have a 1's column, but then instead of a 10's column, we have 16. The next column is 256. So these are powers of 16, right? That's 16 to the power of 1. That's 16 to the power of 2. This one is actually 16 to the power of 0. We'll talk about the 0 exponent a little bit later on in the course. But those would be my place value columns. So again, if I've got my decimal numbers on the right, the number 1 is just going to be 1 as well in hexadecimal. Same thing, the number 2 is 2, the number 3 is 3. Because it's base 16, I have 16 symbols. I've got 16 different symbols, so I can put 16 values in my 1's column. Let's just go down a little bit here. If I go down to 9, well, I still use our normal number, our normal symbol 9 to represent 9 in hexadecimal. The problem gets to 10. In the decimal system, we have to use 2 digits to represent 10. In hexadecimal, I'm only going to use 1 digit because I can still fit it in my first place value column. Well, okay, I don't have a symbol for 10. What can I use instead? Well, hexadecimal uses some letters. So 10 is going to be represented with A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So because it needs 6 more symbols, because the base is 6 larger, I need to borrow 6 letters. And then when I get to 16, well, now that's going to be 0 in the 1's column, and then 1 in what we call the 16's column. So if you see the number 10, we interpret that as 10 in decimal, but in hexadecimal, this actually represents the number 16. Same thing if I wanted to represent 17, well, that's 1 in the 16's place, and then 1 in the 1's place. So it's an interesting, different system. Computers often take also inputs in hexadecimal, because each hexadecimal number contains 4 binary digits, because 16 is 2 to the power of 4. So if you're interested in computers, how they work, how they're running behind the scenes, they're often going to work in binary or hexadecimal rather than decimal. So decimal works really well for humans because we have 10 fingers. but computers work really well in terms of powers of 2. So binary is a power of 2, 2 to the power of 1, and hexadecimal is a power of 2, because that's 2 to the power of 4. Now, I don't know, I'm interested. If you're like a three-toed sloth, would you prefer working in base 3 because you can only count your 3 toes? I'm not sure three-toed sloths do a whole lot of counting. So that's just another video on number systems. If you want to practice converting some numbers to binary and hexadecimal, I will post those in our content section, and maybe I'll have you try a couple on your upcoming number systems quiz as well. Okay, that's all for now. Thank you.